to just find out this area. So I can say, look at here. These are 4 runs that I would have around this, like we had 86.8, like 86.8. Ignore these numbers. I'm going to talk about them like quickly. But these are the center points, but I'm going to talk about that. So these are the 4 runs that I would have, like 4 factorial new runs that I would have around this. So, and I'm going to call them like run number 11 to 16, and it's going to be second, first order design. And this is the, you can look at it. So it's like that. We would have the run from 11 to, let's say, 16. I'm going to have my time and temperature, x1 and x2, and then it's -1 and +1. It's very similar to this because we said that we are like the square run that we would have. And then we are going to run the experiment again, and we are going to find the new yields, like new responses, as I said. So when you find these operating conditions, you would need to run your experiment to get these yields. And then let's say for here, I would just write down 2 center points. We had like many center points so far. And then don't forget to update your error variance estimated by the pooling our previous estimate. So because you added 2 more center points, right? And we had 3 before, so it's going to be 5 center points so far. So we are going to find out the S2 of the current, which is 4.21, and then we can pool it with the previous estimate that we had, and we are going to find out 4.07. It's very similar to the one that we had before. Before it was 4, right? But the degree of freedom is 3, so we increased the degree of freedom, which is a good thing. So we fit the linear first order model, and it's going to be the same method as before. So I have the Y estimate. So it's like this. We found the first order model, and then found it, oh, there is no curvature. So we could find a vertical line for it to find the steepest ascent path to go to closer to the optimum area. And then when we went closer to the optimum area, what we have done is that you would design a new experiment, like design new runs for yourself. And then you would need to find a new model for it, right? And the same method that we had, you just go and look at page 14 on this example. So you can see that we're going to find out beta 0, beta 1, beta 2. We have positive and negative like effects and everything. And then like we would get the interactions. Here, the interaction, look at this, 4.88. So the interaction here, in fact, it's huge when you compare to this 2.0.25, 1.32. So probably we have the curvature. And after we found that this interaction and the curvature test, we would say, okay, so this is the like beta 1.1 plus beta 2.2. And for finding out this one, you will say, okay, so let's say whatever you have for the average for the factorial ones, like the 4 points, and the average at the center point, you would subtract them, and we're going to find out the curvature value is really huge, like -5.28. So the first order model is not adequate to represent the local response function for the new area that we found, like the local funds that we find. So what are we going to do is that we can do the lack of fit test, by the way, as well. So some of us score of the residuals, and then some of us score of error, some of us score of the pure error. We found it for the pure error, 4.21. And then we are going to find out the sum of square of the lack of fit, which is 132.16. So, and then F observed, we compare it with the F from the table. You can see this 16 is a lot larger than the 9.55. This is from the table. So here, even this, we have a significant lack of fit exit. So it's like it confirms the previous result that we had from the curvature test, like from the average of the factorial response minus the average of the center points. So what does it tell us? It tells us, okay, go ahead. You need to find out to add the curvature terms, which is the quadratic terms. So what's next? the first order model has been shown to be inadequate. We have significant lack of fit exists, so we would add alpha star. So we have curvature, and when we have curvature, it means that okay, you need to add some value more than that +1 -1 that would show that curve that you have, and like it's like that. I consider something like this, but in reality, I have my model comes to here, like I have a surface like here, and then I need to add alpha, right? To and whenever we talk about the alpha in like CC central composite designs, you would consider as alpha like minimum of the alpha was square root of the like 2, which is 1.41, right? So what are we going to do is that we have the gradual like development of the CCD parts, as you can see. Okay, look at here. So we are adding these points, these 4 points. You can see that these are the axial points. This is central composite design. So we just developed the central composite designs here. Hopefully it's very interesting to me. Hopefully you find it interesting as well. You see that how we, first of all, we were here. It's like considered like you, in reality, you had your counter was here. It was like a plane like this, and then it was like this, right? And you want to move to the part that is like you have the curvature. It's like this. Look at here. So at the beginning, or like you can rotate it, we were here, but then we moved here in this area, and now we are working on this. We are trying to find out the curvature and everything here. So here we have the alpha, we add runs, like new runs to our system from 17 to 22 here. And you can see it here. So you have the alpha as 1.41. You can go and check the table that we had on in the previous chapter, chapter 8. You can see that the minimum value of the alpha that we consider is 1.41. And then here is how we write it down when we have the alpha, because we said that this is a two factors. And when we had 2 factors, it was like alpha and 0, right? Minus alpha and 0, and then 0 alpha minus 0 minus alpha. It doesn't matter how you write down these ones. The only thing that matters is that your temperature and time should, like when you're encoding them, it should make sense. Like it should be the same as like with the coded ones. And then I have the X1 and X2. I wrote down these, like these are the coded one. You're going to run your experiments again, and then you would find out these yields. Now you have these yields and you have your center points. Let's add 2 more center points. We already had a lot of center points, so we just like that. We already had like 2, and then for this area, right? And then we have 90 and 145, and we found these center points from the if you remember the steepest one, when we were steepest ascent, when we were adding like the value to our X1 and X2, so we found these center points over there. Okay, so we fit the second order model and least square on the data from run 11 to 22. It's very similar to the nonlinear models, right? When you're looking at it, it's polynomial. And then for the all runs of the central composite designs, from 11 to 22 is like 12 runs. So we had when we are talking about the central composite design, be careful here, we consider those 4 points that we had before in our like square ones that we had. And then we're gonna write down our model. Let's test it. For the lack of fit test, you have the model, we can find out the Y estimate, and from there we can find out the sum of the square of the error or the residuals. We found the sum of the square of the error, degree of freedom of it, sum of the square of the pure error, and then we had 2 center points before and 2 here, so it's going to be 4 center points, right? And then sum of the square of the lack of fit, which is going to be this one minus this one, and then we're going to find out the F. Look at here. The F here, F observed is 2.1, and the F from the table is 9.28. So what does it tell us? It tells us that this model, there is no lack of fitting anymore with this new model. So this is a good model because F observed is less than the F critical. So there is no evidence of lack of fit, so we can accept this model. Then what are you going to do is that, so this is what we want in this course. We want to be able to generate this model. So right now, you know that like how you would go, like what's the procedure, like the general approach that you would do. Of course, if I want to ask you in your exam, I'm going to give you like a small portion of it, and I'm going to provide the response to you. But that's how you would design your experiments when you want to looking for the you want to go with this response surface model. So we find this one, and this is our response surface, right? This is our response surface model. It has a quadratic, it has the interaction, the lack of fit perfect, it's really small comparing to the F of the table. So we can say, okay, this is my model, and you can uncode it, that one, and say that the X1 and X2, and then write down the general regression model for it. And then we would draw, like we would have the counterplot of the response surface, and you can look at it here. It's that 82, 84, like 87. You see these numbers, like these counters that it's gonna go. It's increasing this way. And when we go, like we would go to the 87, 91, but still, be careful. We haven't found the optimum here. So finding the optimum value is something that I want to ask you, like there is no assessment for it in this course. So in this course, we want to learn the methodology of the response surface. How can we develop the response surface model? So after I finish this chapter, there's just 1 or 2 slides, and I'm going to continue talking about this example today. And then you're going to see that we just add our constraints for this one. It's going to be it's going to be in the optimization course, but it's very simple. It's just that I'm going to show you. I thought that it's just 1 or 2 slides, and it's good that if I show you. But for our course, it's up to here. Like I want you to be able to understand that how can we find out this response surface equations.